طيب السلام عليكم. Inshallah, today we will be starting chapter 6, which is the second law of thermodynamic, and inshallah we'll have application on the second law of thermodynamic in chapter 7, which is the last chapter of this course, thermodynamic 1. طيب, the objective of this chapter, inshallah, today we'll introduce to the second law of thermodynamic and see the difference between first law and second law of thermodynamic. We'll identify the valid process. Actually, a valid process should satisfy both first and second law of thermodynamic to have a valid process. Also, we'll discuss what's called actually the thermal energy reservoir, which is a system actually of big capacity, big mass capacity, so that it can absorb actually a finite amount of energy without having temperature difference. We call this as thermal energy reservoir. Also, inshallah, in this chapter, we'll be talking about reversible and irreversible processes. And also, we'll have the main application of thermodynamics, the main two applications. Application to the heat engine, which is a system that converts heat into work, like gas turbine, steam power plant. We call those systems as heat engine, which absorbs the heat and converts this heat into work in a heat engine like a steam turbine or a gas turbine. The other main application, which is the refrigeration and the air conditioning system and also the heat pump system, all of these systems are working on the same cycle, and they work actually based on the principle of converting the work into heat, not the heat into work. So in case of refrigeration and air conditioning, we cool down a medium inside the evaporator, and then by absorbing the heat inside the evaporator, and then we reject the heat inside the condenser. In case of heat pump, it is the same cycle like the air conditioning system. Like the air conditioning system in your car, it can be hot or cold. Also in your house, we have the air conditioning split unit. It can work as air conditioning to cool down the air, or it can work as heat pump, as a heater in this case. The idea here actually of the refrigeration cycle or heat pump cycle or air conditioning cycle, that we absorb the heat. In case of refrigeration and air conditioning, we absorb the heat either from food compartment or from the air inside the room or something, and then we reject this heat in the condenser through the air conditioning unit. In case of heat pump, when you want your air conditioning system to work as a heater, in this case we just flip it to have the condenser inside, which rejects the heat. Then it will reject the heat to the inside of the system. And we have the evaporator outside. So it will absorb the heat from outside and reject it inside. Like the case of winter or something, you can just flip the air conditioning unit to have the condenser inside. Then it will absorb the heat from the surrounding air outside your house. And then it will reject this heat to inside of your house. And in this case, the air conditioning system will work as a heater in this case, or what we call actually a heat pump. Anyway, inshallah, we'll be talking about the differences, those differences, inshallah, later on. We'll talk about the two statements of second law of thermodynamics. We have the Kelvin-Planck statement, which is applied to the case of heat engine. And also we have another statement for the second law of thermodynamics, which is called actually Clausius statement, which is applied to air conditioning, refrigeration, and the heat pump system. Also, we'll discuss, inshallah, the concept of perpetual motion machine, which are machines that are in violation either of the first law of thermodynamics or the second law of thermodynamics. So actually, those machines are just actually virtual machine. They cannot come actually to operation. We'll apply also the second law of thermodynamics for some cycle and cyclic device. As we said, will apply to heat engine and refrigeration and the heat pump system. And then actually we will relate through thermodynamics, second law of thermodynamics, we will relate actually the variation of heat transfer based on actually the absolute temperature scale. We'll see the relation between heat transfer and the absolute temperature based on the second law analysis. Also, one very important characteristic of the second law of thermodynamics is the Carnot cycle. Carnot cycle is a cycle that is reversible. It actually consists actually of a number of ideal reversible processes. That means actually the system does not have any kind of friction or any kind of losses. So in this case, when we calculate the efficiency of any system based on Carnot cycle, this efficiency should be the maximum value, because in Carnot cycle we assume actually we don't have any kind of losses. All processes are reversible. Reversible means actually we don't have any kind of losses within the system. So that means the efficiency of the system should be maximum in this case. Then we can apply the Carnot cycle for heat engine, refrigeration, and heat pump. Then we can calculate actually the maximum efficiency of those systems. Then we can compare it with the actual value. So if the actual value efficiency of the system is very close to the Carnot value, which is the maximum value, that means actually this system is a very efficient system and its efficiency actually is high in this case. But when we have deviation, large deviation between the actual efficiency of the system and also the Carnot one, the one calculated by the Carnot cycle, that means we have a large amount of losses within this system. And inshallah, we'll see this by applying actually the Carnot cycle to heat engine and refrigeration and heat pump system to calculate the efficiency of heat engine. And for refrigeration and heat pump cycle, air conditioning cycle, we don't calculate, we don't evaluate the performance using efficiency. We evaluate the performance of those systems using what we call actually the coefficient of performance. So efficiency is applied for heat engine, and coefficient of performance is the parameter to calculate actually the performance, evaluate the performance of refrigeration and the heat pump system. Inshallah, we'll see all of this, how we can calculate the efficiency and the coefficient of operation. As introduction to the second law of thermodynamics. Second law of thermodynamics, it states actually any process has to proceed in a given direction, and this direction cannot be reversed. Like as we said, if we have hot cup of coffee, so the heat can transfer from the hot coffee to the surrounding air, but actually this process cannot be reversed because heat cannot or energy cannot be transferred from actually low temperature to high temperature. So the heat can transfer from the high energy quality from high temperature to low temperature. Also here, if we have a paddle wheel or something, then in this case we have input shaft power. This input shaft power can be converted to heat. It will move actually the fluid inside, and it will accept this work will be converted to kinetic energy, and this kinetic energy will be dissipated in friction between the molecules themselves and between the molecules and the wall. And at the end, actually, this input work can be converted to heat. But if we reverse the process, if we added heat to the air inside or to any fluid inside, this shaft cannot be rotated because we cannot convert the heat into work unless we have a heat engine, like gas turbine, steam turbine, or internal combustion engine, like the engine in your car. We burn the fuel to have heat. Then inside the engine, we can move the pistons, then we can convert this heat into shaft power, in this case, to drive the car. So to convert the heat into work, we have to have what's called a heat engine, and it should work on a cycle in order actually to generate continuous work. But adding heat actually outside the heat engine, we cannot move the paddle wheel to convert it to work. So that means this process has only one direction. It can be converted work, it can be converted to heat, but heat cannot be converted to work unless we have a heat engine. Like this also, if we have high resistance coil, electric coil, if we pass electric current in this case, then this electric work can be converted to heat. So actually this high resistance coil. But if we heated up this coil, actually in this case we cannot generate electrical power in this case. That means any process has a direction, has to proceed in a given direction. This direction has to satisfy the first law of thermodynamics, and also it should satisfy the second law of thermodynamics. First law of thermodynamics, which deals actually with the quantity of energy. Any process should satisfy the first law. Energy into the system minus energy out should equal to the change of energy within the system itself. This is actually the energy balance based on the first law of thermodynamics. Second law of thermodynamics, we say actually any process has a direction, and second law of thermodynamics deals with the quality of energy. Energy also has quantity and it has quality. So if we have a system under high temperature, we say this system is having actually high quality of energy, so that actually this energy can be transferred to another system at low temperature, which is a low quality of energy in this case. And this direction actually of energy transfer should be actually from high energy potential or high energy quality to a low energy potential or low energy quality in this case. So the second law of thermodynamics states that any process should proceed from high energy potential to the low energy potential. As I told you, we have what we call actually the Carnot cycle. Carnot cycle calculate actually the maximum efficiency of the system, or we call it actually the theoretical limit, because we assume actually all processes are reversible, we don't have any kind of losses. So in this case, if we calculate the efficiency based on the Carnot cycle, based on the second law analysis, then in this case, this efficiency will give us the theoretical limit of this system, or the maximum value of the efficiency of this system. Then we can compare it actually with the actual value and see actually how much is the difference between the actual efficiency of the system and the theoretical one, to give an idea actually about the losses within this system. If it is applied in chemical reacting medium, in this case actually if we apply the Carnot cycle to this engine, it will give us also an indication about the degree of completion of the chemical reaction, how much is the system is efficient in converting the fuel into heat release in this case. Okay, Shabab, as we have known that any process should satisfy first and second law of thermodynamics, should be the energy balance, energy in minus energy out, equal to the change of energy of the system while this process. And also any process energy transfer should proceed from the high energy potential to the low energy potential. Let's define what we call the thermal energy reservoir. Thermal energy reservoir is a system with big mass, which has actually have a large thermal energy capacity. Thermal energy capacity is the mass multiplied by the specific heat. So if we have a big system like river, ocean, lake, or the atmospheric surrounding air, those are big systems with big mass. That means those systems can absorb actually any finite amount of heat without having temperature change. So if you reject some hot exhaust gases from the engine of your car in the surrounding air, in the surrounding atmosphere, will the atmospheric temperature be raised? The global temperature will be raised because of your car? No. So we can call in this case the atmospheric air as a thermal energy reservoir in this case. It can absorb actually a finite amount of heat without having a change actually in the temperature. Like this, if we reject some hot water to the lake or ocean or something, that will not result actually in temperature rise of the water inside the lake or inside the ocean. So we can consider them also as thermal energy reservoir in this case. Thermal energy reservoir can be a source of heat. Okay, it can give a certain amount of heat without temperature rise, or it can absorb a certain amount of heat without also a temperature rise in this case. We said the two main application of thermodynamic. We have one main application in what we call actually heat engine system, and the other application is the refrigeration, heat pump, and also air conditioning system. They are working all on the same cycle. So this is the second application. Heat engine converts the heat into work. Refrigeration, air conditioning, and heat pumps are working on the same cycle, and they convert actually work into heat in this case. But both heat engine and refrigeration, air conditioning, and heat pump cycle, all of them are actually working on a cycle to generate actually continuous work in case of heat engine, and also to absorb the heat continuously, actually absorb the heat or reject the heat from refrigeration or heat pump system continuously. Then in this case, the system has to work on a cycle in this case. Okay. So in case of heat engine, it converts the heat into work. So it receives the heat actually from high temperature source. We call this actually as thermal energy reservoir. It absorbs the heat from high temperature source. Heat is added. Part of this heat is converted into work inside the engine. This engine is about like the engine of your car. We add the heat, burn the fuel, then we have heat is added in this case. Then this heat actually pushes the piston under high pressure and high temperature to move. Then we can convert this heat into mechanical shaft power to move your car. Or like a steam turbine, we have steam under high pressure and high temperature. We burn the fuel to convert the water into steam. Then this steam under high pressure and high temperature can expand inside the turbine to generate shaft power. So part of the input heat from high temperature source, whatever this source, This heat is converted to work to generate shaft power, and then actually some heat is rejected to the surrounding air in most of the cases, actually at a low temperature. In this case, we call it actually a low temperature sink in this case. So the idea of the heat engine is to convert the heat into work. And in any case, actually, we have to have a working fluid in this case. So any heat engine, we should have a working fluid. So in case of a steam turbine, the working fluid is steam. We add heat to the steam, to water to convert it to steam. Then in this case, this steam expands inside the turbine, then we can have shaft power output. And then actually we take this steam and cool it down in the condenser, and then we repeat the cycle again. So in this case, we have working fluid is just actually circulating inside the system. Okay, so any heat engine should have a working fluid in this case, and also it should work on a cycle to convert the input heat into the output, into an output power in this case. Here, Shabab, is an example of a heat engine, which is actually the thermal power plant or a steam power plant. The steam power plant, the whole plant actually is considered as heat engine. So heat engine is a device actually in which actually we convert the heat into work, and this system actually is working on a cycle in this case. So the heat engine, so if this is the engine, it receives the heat actually from a high temperature source. This source actually is existing at high temperature, that's why we call it actually Q high. Then part of this heat actually is converted to work out, and actually the remaining part actually of this heat is rejected at low temperature sink. That's why we call this heat rejected as Q low in this case. So the heat engine converts the heat into work out in this case. And as an example for the heat engine cycle, should work on a cycle anyway. Any heat engine should be working on a cycle. We give this example, the steam power plant. In a steam power plant, we have pump that actually takes the cold water and then actually pressurize this water to the pressure of the boiler. So it raises the pressure actually of this water. Here actually inside the boiler, we burn the fuel to have actually heat release at high temperature. Then we take this heat actually to be added actually to the water inside this boiler. Then this water will be converted to steam under high pressure and high temperature. Then we can just take this steam to just expand inside the turbine. Then we can generate actually shaft power of this turbine in this case. But the steam leaving, as we said before, leaving this turbine, usually we have saturated mixture of liquid plus water. Then we need to return back to the same initial state. We have liquid water in this case. Then we have to reject this heat inside the condenser. So usually inside this condenser, we have actually a kind of cooling water is coming. Then actually it can absorb the heat. This cooling water can absorb the heat from this steam. The heat is absorbed at low temperature. That's why we call this heat is rejected at low temperature. We call it as actually Q low. Now this saturated steam will be converted back to water, to the initial state. So the condition actually for any system to work on a cycle that we have to start from one point, do all of these processes, you have to get back to the same initial point so that we can actually repeat all of these processes again, and the system can work on a cycle to generate continuous shaft power in this case. Otherwise, actually, if we are not returning to the same initial point, in this case, actually, the system will not be able to work on a cycle to generate continuous work. The system will stop in this case. So that's why the steam here, under saturated mixture state, we cool it down so that actually we reject this heat. This is heat actually. Steam still have some heat. And this heat actually is part of the input heat. We have to keep this heat, but we cannot. We have to reject this heat so that actually we can get back to the same initial state. This is something does not relate actually to the losses, friction losses or something. This is related to the concept of operation on a cycle to generate continuous work. In this case, we have this heat here, but we have to reject it. We have to get rid of it so that actually we can get back to the same initial point. This is the concept of operation on a cycle. Then we can repeat the processes to generate continuous shaft power in this case. Okay. طيب, to calculate the efficiency شباب of this system, usually this pump is deriving actually using part of the energy, part of the shaft power actually produced with this turbine. So in this case, the network of this cycle should equal to the work out of this turbine minus the work input inside this pump. Okay. So what we get from this cycle is the network, which is the difference between the power shaft power of the turbine minus the power required to drive this pump in this case. طيب, as the system يا شباب working on a cycle, we said before, for system working on a cycle, we said energy in, first law of thermodynamics, minus energy out will equal to the change of energy of the system. And this change of energy of the system is energy final minus energy initial. But we have the final state is the same as the initial state. So that means the change of energy of the system should equal to 0 in this case. Okay, right. As the system, that means energy in minus energy out should equal to 0 in this case. But what kind of energy transfer in or out in this case we have? We have energy can transfer by heat, air, and boiler and the condenser. And also energy can transfer in the form of work, like in case actually of pump and a turbine in this case. But do we have mass transfer in this case? No, we have just working fluid is circulating inside. But we don't have any mass added or any mass actually leaving this system. If you look at this system, we don't have any kind of mass in or any kind of mass out. It is the same amount of water. We just actually raise its pressure, convert it to steam, then we can actually get saturated mixture here, then we can cool it down, and then we get back again. We don't have any mass transfer in this case. And based on this, we set this area relationship. Energy in minus energy out will equal to 0 for a system or a cycle, and the energy in or out for heat transfer. That means in this case for any system working on a cycle, that Q net, the net heat actually to the system, should equal to the net work out of this system. And the Q net is equal to Q high minus Q low, Q added in the boiler minus heat rejected in the condenser in this case. This is actually Q net. This should equal to work net, which equal to the work out from this turbine minus the work input from this pump in this case. And this is actually for a system working on a cycle. We should have net heat to the system should equal to the net work out of this system. Or Q high minus Q low should equal to work out minus work input to this system. But to calculate the efficiency of this system, of any heat engine system, the efficiency should equal to what we get the desired output from this system, so the thermal efficiency of any heat engine. The thermal efficiency, we call it eta thermal, should equal to the output, the desired output from this system, divided by actually what we give to this system, the input power. We call it input power or the output of the system. This is the output power, net output power divided by the input power in this case. Okay, but what we get from this system is what? The network. What we get actually is the network, not the work out of the turbine, because this work, part of it will be consumed in the pump. What we get is the network, the difference between the work of the turbine and the work of the pump. This is the output of this thermal cycle. We call it a heat engine in this case. Divided by what we give to the system, the input power to the system is the heat added here through burning fuel. So in this case, we burn fuel inside a furnace, and then actually we take the heat released actually from this furnace to boil the water and convert it into steam in this case. Okay, so what we give to the system is the fuel energy, or what we call it actually as Q high. So the thermal efficiency of any heat engine equal to the network output divided by Q high. But we said that Q net is the same as work net for a system working on a cycle. Q net is the same as work net. I just replace it in this definition of the efficiency. So in this case, that should equal to work net which equal to Q net, as the system is working on a cycle in this case, divided by Q high. And the Q net is equal to Q high minus Q low. This is divided by Q high. That means the thermal efficiency will equal to 1 minus Q low divided by Q high. And this is the definition of the thermal efficiency of a heat engine. The thermal efficiency of a heat engine equal to work net divided by Q high, heat added at high temperature, and that should equal to work net is the same as Q net. It will be Q high minus Q low divided by Q high, or it is equal to 1 minus Q low divided by Q high. Q low is the heat rejected from the system, like this steam power plant, heat is rejected in the condenser. Q high is the heat added under high temperature, which is the heat added in the boiler in this case. Okay. طيب, look here, شباب. This is the definition of the thermal efficiency we just defined, equal to 1 minus Q low divided by Q high. Q low is the heat rejected in the condenser. So if we are able to reduce this value of Q low, then in this case we can increase the efficiency. And that's why we may have a heat engine system that have better efficiency than another system. So here in this system, we have the network output is equal to 20 kilojoule. Here in this system, the network output is equal to 30 kilojoule. But actually for the same input heat, 100 kilojoule. That means the efficiency here actually of system number 1 will equal to the network output, which is 20 over input 100, so it will be 20%. But the thermal efficiency of the other system will be higher in this case, will equal to 30% in this case. Okay. Can we show up here, if you look here about this drawing here, we said here this steam is saturated mixture, and still it have some heat, which we reject inside this condenser. If we don't have this condenser, we just excluded this condenser. So that means we will keep this Q low. Q low will equal to 0. So 1 minus 0, it will be actually 1. That means the efficiency equal to 100%. So why we should reject this heat inside this condenser? It will reduce down actually the efficiency. But actually this is the concept of operation of a cycle, like what we said. This pump cannot handle saturated mixture of liquid plus water under high temperature. It can handle only liquid water. And this system to work on a cycle, we have to get back to the same initial point. The same initial point, which was actually liquid water. So we have to reject this heat so that we can retain back the same initial point. Then this pump can handle this water, and then we can repeat this cycle. Then we can generate actually continuous work out of this system. So if we just remove this condenser, the system will not be representing actually a cycle, and it will not be generating continuous work. Just it will be doing actually those processes for one time, and then the system will stop. So that means we cannot design a heat engine with efficiency equal to 100%, because we have to reject some heat inside the condenser. And this heat rejected is part of the input heat. So that means we have some energy is lost from the system. So that means the efficiency in this case should be less than 100. And this is actually the Kelvin-Planck statement, which is the first statement of second law of thermodynamics applied to any heat engine. That it states actually that you cannot design a heat engine with efficiency equal to 100%. The efficiency should be less than 100 because we have to reject some heat from the system, so that the system can retain the initial state and it can work on a cycle to generate continuous work. So Shabab, the efficiency is less than 100, not related to the losses within the system itself only. It is related to the concept of operation on a cycle. We have to reject this heat to get back to the same point, then we can repeat this cycle. To understand this Shabab example, let's look here. If we have a load here at a given stop here inside this piston, and I want to raise this load to actually to the second stop here. Then in this case, we have gas inside, we'll be adding heat. Let's say from high temperature source, from 100 degrees C to 30, we'll be adding heat. So the piston will be moving, the gas will expand, and it will force the piston to move. Then we can take this load at the second stop. Now I want to repeat this process. I want to work on a cycle. I want to have another load from down there and get it up there. What should we do in this case? Still the gases are hot, at let's say at 90 degrees C. So that means I have to reject this heat. Then this gas, it will be actually, in this case, cool down. It will contract in this case, and in this case, the piston will fall down actually to the lower stop in this case. Then we can repeat this process, add heat again, and then we can raise this load again. But if you stopped at this point, stuck at this point, and you say, I have some energy, I don't like to lose this energy. It's okay, just stay here, and the cycle will not be repeated. To repeat this cycle, we have to reject this, we have to lose this heat. It's okay. So this is related to the concept of operation on a cycle, not related to the friction within the system. And this is actually the Kelvin Planck statement for any heat engine. It states actually that it is impossible for any device that can operate on a cycle to receive heat from a high temperature source and convert this heat, all of this heat, into output work without rejecting heat. So this is actually impossible design. We cannot design a system working on a cycle without heat rejection. But as we should have some heat is rejected from the system, that means we should have some losses of energy. That means the efficiency should be less than 100. And the rephrasement actually of this statement is this statement that you cannot design actually a heat engine with efficiency equal to 100%, as we should have some heat should be rejected from this system. Okay. Inshallah, next time we'll be talking about the other statement, which is the Clausius statement, which should be applied actually in case of refrigeration and the heat pump system. طيب, look at this simple example. We have heat is transferred to a heat engine from a furnace at a rate of actually 8 megawatt. So this is Q high, 8 megawatt. And actually the rate of heat lost actually rejected to an nearby river is equal to 50 megawatt. This is Q low. And we need to determine the net work output of the system and the thermal efficiency. So we set for a system working on a cycle, Q net is the same as work net. So work net is equal to Q net, which is Q high minus Q low. Q high is 80, Q low is 50. So that means the net work out of this cycle should equal to 80 minus 50, which is 30 megawatt. And the thermal efficiency of this heat engine should equal to the net work output, which is 30 megawatt, divided by the heat added Q high, which is 80 megawatt. So the efficiency should equal to 0.375, or it should equal to 37.5%. And this is actually the efficiency of the heat engine. So based on the second law of thermodynamics, as we have learned it today, we cannot design a heat engine to work on a cycle without having heat rejected from the system, or we cannot design actually a heat engine with efficiency equal to 100%. So if anybody offered you a device that is working on a cycle, any device, any machine, and they said this machine has efficiency equal to 100%. So you have to say very proud, this is actually no. We cannot design a heat engine with efficiency equal to 100%. Okay. So this is actually what we want to say all about today. Inshallah, next time we'll be talking about the application of the second law of thermodynamics to the case of refrigeration and the heat pump system. Assalamu alaikum.